So, hello, physical science. So, you guys have actually already seen some of these slides. We talked about them in a large group this week, but I am just going to make this video so we can kind of have a little review so that lab today will help or sink in a little bit better. So, seismic waves, what are they? So, we have three different types of waves that are produced by earthquakes. The first type is the primary wave or the P wave, and this wave is going to be the fastest moving wave caused by earthquakes. These cause particles in the earth to compress and stretch as the energy moves in one direction. So, when an earthquake occurs, we have the epicenter directly above the focus where the earthquake occurs, and those waves travel away from the epicenter. And when they do, they travel in this motion where they are compressing and then expanding, stretching apart. So here we can see the force is exerted at the left side. It travels, compresses, and on the outside of those compressions, you can see that the earth is expanding just a little bit. Okay, they are our fastest wave. I have a little graph that I'm going to show you here in a second that shows the differences on how P waves travel versus S waves. S waves are our secondary waves, and they're the second type of wave that get produced when an earthquake occurs. So these are our S waves, cause Earth to move up and down as it moves in one direction. And they are one of our slower waves. They do medium damage. So these waves, if I play this video, when we exert a force or we have an earthquake occur, we see that as the earthquake is traveling, so the earthquake occurred over here, the force as it moves causes the earth to shift down and then upward as the wave travels away from that epicenter. So if we play this through, we can see that it travels on. So we have the downward wave and the upward wave. You can watch this a couple different times so you get the idea. But those are our secondary waves. So here's that chart that I was talking about. So P and S wave travel time. So we can use P waves and S waves to determine how far or the location an earthquake occurred at. So here we have this big red line, and it's a shear wave. So a shear wave is just another way of saying an S wave. And then this blue line here, we have a compression wave or a P wave. And those are just talking about how they actually travel. Because like we said in the slides before, P waves are compressed and then stretch as they travel, and shear waves have that downward and upward movement as it travels through the earth. So if we look at 0, 0, 0, 0 is going to be the epicenter or the focus where that earthquake occurred. And we can see right off the bat that the compression wave, the P wave, is traveling significantly faster. It's traveling a greater distance in less amount of time. Because if we look, let's say 5 minutes. So 5 minutes from when the earthquake occurred, we can see that the distance traveled for the compression wave or the P wave is already probably about 3,500 kilometers away from the epicenter, and that's just in 5 minutes. If we look at the shear wave or the S wave, we can see that at 5 minutes, the shear wave has not even traveled 15,000 or 1,500 kilometers yet. It's moving significantly slower. So as time goes on, so as we get from 5 minutes to 10, 15, 20, 25 minutes, we can see that those waves, the distance between those waves, the P wave and the S wave, gets greater. So the greater the distance, the farther away that the actual epicenter was from your location. So then we have our surface waves. These guys are the real destructive waves that cause a lot of issues for coastal cities in Japan. They're the ones that actually cause tsunamis. So we can see only found on Earth's surface. You get the name surface wave, found on Earth's surface, pretty easy stuff. travel in a rolling motion. So if we look up here at this image I have here, it travels like an ocean wave. So you can actually see these waves traveling, almost rolling. If you look at this circle here, it's rolling. See that little dot going around, rolling as it travels through the Earth's surface, through the top layer of the crust. And when these actually occur, you can literally see the Earth shifting like this. And these guys, that's what makes these guys so destructive, is the Earth is literally moving up and down, rolling like the ocean as it goes. And these guys are far and away the slowest wave that we have. So what do we do with these waves? So these waves, S&P waves, they travel throughout the entire globe. So here on the north side of this simple model of the Earth, we have the epicenter at the North Pole. So when an earthquake occurs here at the very North Pole, or anywhere, it could occur here, it could occur here, it just depends on where that epicenter is. The waves are spread out, they travel through the Earth. And as we can see, all of this outer layer here is mantle. It's still pretty much rock. It might be a little bit, you might have a little liquid lava in there, but for the most part, it is a cool rock. So the waves can actually travel through that pretty easy. But as we reach the liquid outer core, we're getting close to that center, we can see that these waves are more or less deflected. So if we look at the yellow lines here are our P waves. Our P waves actually can travel a little bit into our liquid outer layer. But if you look at our S waves, which are our black lines, they are completely blocked by the liquid outer core. So if we were on the very southern tip of the very opposite side from the epicenter on the Earth, we would not in this range be able to feel or pick up any S waves from this earthquake, just because they have been blocked by our liquid outer core and our solid inner core. But because our P waves travel so much faster and have more energy, they actually can penetrate the liquid outer core and the solid core. And there are a few places on the other side of the Earth that we would be able to pick those guys up. So we can use these waves to pinpoint locations of earthquakes. So you can, anywhere you see these lines here, you'd be able to pick up and tell that an earthquake occurred in this particular location. So here I have How Scientists Listen to the Earth. It's a short article. If you would like to look into that, it's actually pretty interesting, but you do not have to if you don't need to. But here we have Listening to the Earth. So when tectonic plates slide past each other, they release S&P waves. We've talked about this. You guys know this. Earthquakes release S&P waves. These S&P waves can be used to detect oil, rock types, and tell us about the Earth's interior. So if I go back to the previous slide here, and we're looking at this image once again, when these earthquakes occur, we can use the way the waves bounce off these materials inside the Earth to tell what's there. So we can tell where oil pockets are or where cave systems are based on how these waves interact with the Earth beneath our feet. So S&P waves used to detect oil types. If you watch this video here, the Earth and any planet actually has its own sound. So I know we talked about a little while ago that Earth itself or space itself doesn't have sound, but that doesn't mean it's still not emitting waves. So if we actually put a radio detector in space, we can actually pick up on these waves and see see and hear what the Earth actually sounds like, because each planet has its own sound that's unique to that. So that's an interesting video that you guys can watch. So I hope this video helped you out a little bit with S&P waves. If you have any more questions, please feel free to ask me or Mr. Anderson. We'd be happy to help.